Accelerating a single subatomic particle to 99.999999% of light speed requires more energy than a freight train in motion. This barrier is a geometric property of spacetime defined by a vertical asymptote. The speed of light in vacuum is exactly 299,792,458 meters per second. This value is a universal constant that remains identical for all observers, regardless of their own motion. The Lorentz factor is the mathematical function governing relativistic changes. It is expressed as 1 divided by the square root of 1 minus the velocity squared divided by the speed of light squared. This factor determines how time and mass scale. As the velocity of an object increases toward the speed of light, the term velocity squared divided by light speed squared approaches 1. Consequently, the value inside the square root approaches 0, which creates a division by 0 scenario at the limit. In pre-calculus, this behavior is a vertical asymptote. As the input velocity approaches the speed of light from the left, the output of the Lorentz factor function increases without bound toward positive infinity. The speed of light is the unreachable boundary. The domain of this physical function is restricted to values greater than or equal to 0 and strictly less than the speed of light for objects with mass. Values exceeding light speed would result in the square root of a negative number. Classical mechanics assumes velocities add linearly. If you run at 10 meters per second on a train moving at 50 meters per second, your total speed is 60. However, this linear relationship fails as we approach the cosmic speed limit. The relativistic velocity addition formula ensures that the sum of two velocities never exceeds light speed. It divides the classical sum by a factor that increases with speed, keeping the result within the valid domain of the spacetime function. Time dilation is a direct consequence of the Lorentz factor. As an object moves faster, time for that object slows down relative to a stationary observer. This is not a mechanical clock error, but a stretching of the temporal dimension. The graph of time dilation shows a nearly flat line at low speeds, where relativistic effects are negligible. Only as velocity exceeds 90% of the speed of light does the curve spike upward toward the asymptote of infinite dilation. We distinguish between proper time, measured by the moving observer, and coordinate time, measured by the stationary observer. The ratio between these two times is exactly the Lorentz factor. At light speed, the coordinate time interval would be infinite. Subatomic particles, called muons, created in the upper atmosphere, provide physical proof of this asymptote. Despite a short lifespan, their high velocity dilates their internal time, allowing them to reach the surface of the Earth before decaying. Length contraction occurs inversely to the Lorentz factor. Objects moving at high velocities appear shorter in the direction of motion. This functional relationship ensures that distances shrink as the observer approaches the speed of light. The graph for length contraction is the reciprocal of the Lorentz factor curve. It starts at a value of 1 and slopes downward, intersecting the horizontal axis at the speed of light, where the length of an object theoretically becomes 0. Classical momentum is simply mass times velocity. In relativity, momentum is mass times velocity multiplied by the Lorentz factor. As velocity approaches the asymptote, the momentum of an object grows to infinity, making further acceleration increasingly difficult. The famous equation E equals mc squared describes the energy of an object at rest. For a moving object, the total energy is the rest energy multiplied by the Lorentz factor, showing that energy and mass are inextricably linked. To reach the speed of light, an object with mass would require an infinite amount of energy. Since the energy of the entire universe is finite, no massive object can ever be accelerated to the speed of light. The asymptote is absolute. Particles with zero rest mass, like photons, must always travel exactly at the speed of light. Because their mass is 0, the division by 0 in the energy equation is resolved, allowing them to exist at the boundary of the asymptote. The speed of light is the maximum rate at which any information or causal influence can travel through the universe. This limit defines the structure of causality, ensuring that an effect never precedes its cause in any reference frame. We visualize space-time constraints using light cones. The cone represents the path of light rays in 2 spatial dimensions plus 1 time dimension. All possible paths for a physical object must remain inside the boundaries of this cone. The upper half of the structure is the future light cone. It contains every event that can be influenced by your current position. The slope of the cone's edge is determined by the speed of light, our cosmic asymptote. The lower half is the past light cone, representing every event that could have influenced your present moment. Any event outside this cone is causally disconnected from you because light has not had enough time to bridge the distance. The space-time interval is a mathematical quantity that remains invariant for all observers. It combines space and time into a single calculation. This invariance is the underlying reason why light speed acts as a fixed asymptote in our universe. As objects approach the speed of light, the light they emit undergoes a relativistic Doppler shift. Approaching objects appear blue-shifted, while receding objects appear red-shifted. This shift includes the effects of both motion and time dilation. At high speeds, the apparent direction of incoming light changes due to relativistic aberration. For an observer moving near light speed, light sources from the side appear to shift toward the front, concentrating the field of view into a bright circle. A fascinating visual effect of the speed of light asymptote is Penrose-Terrell rotation. Instead of appearing flattened, a high-speed object appears to be rotated. This is because light from different parts of the object reaches the eye simultaneously. The Large Hadron Collider utilizes these principles to study subatomic particles. Protons are accelerated to within a fraction of the speed of light. Because of the asymptote, increasing the energy mainly increases the particle momentum rather than its speed. Accelerating charged particles near light speed causes them to emit synchrotron radiation. This light is extremely intense and is used in research to image matter at the atomic level. It is a practical application of high-velocity physics. The Global Positioning System satellites move at several thousand kilometers per hour. Their clocks must be corrected for time dilation using the Lorentz factor. Without these relativistic adjustments, location data would be off by several kilometers every day. Cosmic rays are single protons or nuclei traveling at almost the speed of light. Some possess the kinetic energy of a well-hit baseball. These natural particles demonstrate the extreme behavior of mass near the cosmic speed asymptote. Classical kinetic energy is 1/2 mass times velocity squared. The relativistic version is the total energy minus the rest energy. This formula approaches infinity at the asymptote, showing why classical physics fails at high velocities. For particles with mass, energy is finite only if velocity is less than the speed of light. For photons, where rest mass is 0, the energy is defined by their frequency and Planck constant, bypassing the mass-based asymptotic limit. While light in vacuum is an absolute limit, particles can travel faster than light in certain media, like water. This results in Cherenkov radiation, a blue glow analogous to a sonic boom. It demonstrates light speed varies with the refractive index. The speed of light in a medium is the vacuum speed divided by the refractive index. While the local limit changes, the vacuum speed of light remains the ultimate cosmic asymptote that can never be exceeded by any signal in any environment. General relativity introduces gravity as the curvature of spacetime. Even in curved space, the local speed of light remains the local asymptote. Light always follows the shortest path, known as a geodesic, in this 4-dimensional geometry. Near a black hole, the asymptote is reached at the event horizon from the perspective of an external observer. Time appears to stop for an object falling in, reflecting the extreme dilation predicted by the relativistic functional relationships. If an object could exceed the speed of light, it would move backward in time in some reference frames. This would create causal paradoxes, where an effect happens before its cause. The speed of light asymptote preserves the logic of the universe.
Tachyons are theoretical particles that would always travel faster than light. To exist, they would need imaginary mass and would reach the asymptote from the opposite side, requiring infinite energy to slow down to the speed of light. The speed of light is not just a speed, but a conversion factor between space and time. This mathematical relationship is why we measure cosmic distances in light years. Space and time are fundamentally two aspects of the same fabric. Physics remains the same for all observers moving at constant velocity. This principle of Lorentz invariance is the foundation of modern physics. It demands that the speed of light be an invariant asymptote in all valid physical equations.
By studying rational functions and asymptotes, we gain the tools to describe the universe at high speeds. The vertical asymptote at the speed of light is a profound example of how mathematical limits define physical reality. In classical physics, constant force leads to constant acceleration. In relativity, as velocity nears the asymptote, the same force produces less and less acceleration, as the work done goes into increasing the momentum and energy rather than speed. From the smallest particles in an accelerator to the expansion of the distant universe, the speed of light governs the scale of observation. It determines the size of the observable universe by limiting how far light has traveled since the beginning.
Every time you solve for a limit in calculus, you are using the same logic that prevents a spacecraft from reaching light speed. Mathematics provides the rule set that physical matter must follow without exception. The speed of light is the ultimate cosmic asymptote. It is the boundary that protects causality, links energy to mass, and defines the very geometry of the universe. It is the mathematical wall that shapes our reality.